let's see here. As I promised, an example. I'll start with an example. And I had tried, to do was to work out the ellipsoid from a parametric perspective. So in the videos, I did the ellipsoid in the ellipsoid example, which is the sole example in section 5.5, right, of the implicit method. And it's a really sneaky calculational method. He only has that one example there. And I thought, I wonder how much trouble it is to do the ellipsoid parametrically. And so, yeah, after like a half hour of calculation, it's a mess. And so I'm not going to do that. 'Cause it's just, I'll show you my calculation in the break. It's just unpleasant. And I'm almost right. It's one of those things where like, I was able to like take the calculation I did and match it to what's in section 5.5, but it doesn't quite match. Like I've got an extra sine squared, which means I've got some kind of like stupid miscalculation. So I actually have two examples. I'll start with the easy one. This is an elliptical cylinder, and what we're doing here is calculating the, I'm going to calculate the Gaussian curvature and the mean curvature, all right? And so here, I'm going to look at the cylinder with the equation x squared over a squared plus y squared over b squared equals to 1, right? So like geometrically, it's just one of these guys, right? And it just goes on and on, right? And so a natural parameterization in this case is just to use a cosine u, b sine u, and then v, right? Because that is a patch on this elliptical cylinder, right? You plug those parametric equations in, it works, right? Z is free. And so once we have that, we can calculate the partial velocities. So xu is minus a sine u, b cos u, 0. Xv is 0, 0, 1, right? And so just let me just kind of recap briefly where we're going. Our goal is to calculate, the warping functions E, F, G, W, which is the square root of E, EG minus F squared. It's also the length of XU cross XV. This, and the L, the M, and the N, because once we have those, then there are formulas for the Gaussian curvature and the mean curvature, which we derived in the previous lectures, right? So, great. So here's XU, here's XV, and XUU. What's XUV? What's XVV? XUU is minus a cos u minus b sine u, 0. XUV, well, that's 0. XVV, 0. Right? So then, all right, so the question is, how are this alphabet soup of formulas, how's it work? Well, E is XU dot XU, right? F is XU dot XV. G is xv dot xv. And of course, the unit normal is xu cross xv divided by, well, w, which is the length of xu cross xv. So let's see here. I do need to calculate xu cross xv. What's that? Oh, I hope not. Oh, let me cheat. Xu cross xv works out to b cosine u, a sine u, 0. Now, you tell me if I'm right or wrong. How can you check? Take the dot product of that with the partial velocities, right? So like dot product of this with xu, we've got minus ab sine cosine plus ab sine cosine. Good, that's 0. And this dot, well, dot with 0, 0, 1 is 0 as well. So it's perpendicular to both. We're good. Now, so I'm just going to stick these over here for safekeeping. This is E, this is F, this is G. Of course, that's the unit normal. We also have the L, which was XUU dot U. M was XUV dot U. N, which was XVV dot U. These we derived in the previous lecture. Plural lectures, I should say. Okay, so let's write them down. What's E equal to? You guys tell me. Dot product of this with itself. So we've got a squared. Mm-hmm.
b squared cosine squared u 0.
Right. And F?
0.
Yep, that's 0 because, exactly.
And then the other way around. Is it G is v cross v dot v?
V dot V, right, which is,
A squared cosine.
oh no, V. Yeah, I'm almost of the opinion, like, using U and V here. I don't know, I always have this. U and V don't look enough different, you know? It's unfortunate.
A squared plus b squared in it.
What's that?
Can E not be reduced to a squared?
No, because A and B are not the same. We need it to be the same so we can factor out the sine squared plus cosine squared. So, yeah, if A and B were equal, then that would just become A squared. Absolutely. Okay, so what's the L? I guess I should say what W is. W is the square root of b squared cosine squared u plus a squared sine squared u. All right? And that's the length of xu cross xv. That's the normalization factor for the unit normal. O'Neill does not always use W. He only has W appears on like one page in chapter 5 somewhere, but it's a useful letter to invent because this is, you know, if you've got a problem where this is the expression which is W, it's really nice to write W rather than writing that formula 10 times in your work.
Why is it 1? Why is there another 1 in that parameterization?
No, 1.
Yeah, when you're doing the unit, the W, then why is it just a squared?
Oh, because it's the length of the xu cross xv. It's the length of the normal vector field. Dividing by that gives us the unit normal vector field. And so, free fly. L, what's L equal to? U dot.
The unit vector field.
Right. Now,
Is that what it's called?
yeah, the unit vector field. The unit vector field is 1 over W. This vector right here.
So that's a perpendicular line.
So this one dot that one. We've got 1 over W, right? And then we get minus AB cosine squared. And minus AB sine squared. Hey, look, finally some trigonometry to do, right? So that just simplifies to minus AB over W, right? What's M equal to? M is xuv dot u. So that's easy. xuv is 0, so it's 0. And likewise, n is xvv dot u. Well, xvv is 0, so it's 0. So m equals to n equals to 0. All right. Now we have collected this alphabet soup, if you will, and from this we can, construct the Gaussian curvature and the mean curvature. There's formulas that we've derived. So let's see here. It's the partial acceleration. It's just the second derivative with respect to u. Yeah, and likewise these are all partial accelerations, if you will. And
So what's the partial, why is that the partial acceleration of UV? Is that how you, by dot product using?
this,
Yeah.
you just differentiate either xu or xv with respect to v or with respect to u. Either way, you get 0. So it's just usual partial differentiation. I like calculus 3. Let's see here. Let me go ahead and put the formula for the Gaussian curvature up here. It is ln minus m squared over w squared. And the mean curvature is Glenn, GL plus EN minus 2FM divided by W squared. Oh, excuse me, by 2W squared. Right, so I'm going to leave those up here. Okay, so you said, so thus K equals to 0 and H equals to what? Mm-hmm.
Is that 2 or partial differentiation?
2. That's a 2.
Yeah, 1 W's cancels out, so you get 2 W's.
Oh, I think they multiply. I think you get a W cubed. Because you get a W squared in the denominator.
Yeah, but that one's in the denominator. The G,
Well, it's in the denominator of the numerator, which means it multiplies, like the G and the L.
yeah, it's essentially multiplying. When you take the reciprocal of it.
We've got 1
Oh, you're right. Yeah.
times minus
No.
a.
Wait,
1 times minus AB over W. That's the GL term. These two are 0, right? And then divided by 2W squared.
No, yeah. That was bad. What is the drop?
Yeah, we get minus AB over twice W cubed. Now W, just to make it explicit, is B squared cosine squared U plus A squared sine squared U all to the 3/2 power. And that's the Gaussian curvature here is 0. And the mean curvature is this thing here.
Why are you in a denominator here? So, yeah, so AB over W, right? And then it's multiplied by the reciprocal of that, which would be square on the bottom.
Well, w is the square root of b squared cosine squared plus a squared sine squared, so we have 1/2 to the cubed is 3/2. It's, the w is here, so it's all of that to the half power, and then we're cubing it, so. Now, just to draw the picture, now does this make sense that the curvature is 0? What kind of surface is an ellipsoid? Well, this isn't an ellipsoid, this is an elliptical cylinder, right? Does it make sense that the Gaussian curvature is 0? Well, remember, so if the Gaussian curvature is 0, the surface is said to be flat, right? This is an example of a flat surface. So that term, flat, doesn't mean maybe what you think it means, right? I mean, on the other hand, the mean curvature is definitely non-zero, right? So we're going to talk more today about what we mean by flat, why we say that that's flat. That means that, in some sense, if you were an inhabitant, if you were somehow an inhabitant of, if you were somehow living on that elliptical cylinder, you would not be able to detect that it's actually curved. For all intents and purposes, it would seem like a flat space to you.
Like how the Earth is curved, but we don't perceive it as curved.
But the Earth is, we could perceive the curvature of the Earth if we made a sufficiently large, triangle.
Yeah.
You could tell.
But I'm saying, like right now, the Earth looks flat.
That is true. I mean, the curvature is very close to 0 because the Earth's so big. That's true.
That one time maybe ever going?
Yes, 1 times. Sorry. I mean, it's GL. It's the GL term. But here's why this makes sense. The elliptical cylinder is a ruled surface, right? You can form the elliptical cylinder by taking a vertical line, right? You can take a vertical line and you just move it around in the shape of an ellipse, right? That's how you can sweep out the elliptical cylinder using a line. So it's a ruled surface. All ruled surfaces have curvature 0 because the principal curvature in the direction of the line is 0. And the Gaussian curvature is always the product of the principal curvatures. So if one of them is 0, the product is 0. And so it makes sense that we found 0 curvature here. Another check on this, what would happen if we put A and B both equal to little, like big R? A equal to B equal to R. What do you get? What's this expression become? Yeah, negative R squared. And then we can do your simplification, right? We get sine squared plus cosine squared.
So over 2.
Right, so we get minus R squared over 2, and then that's R squared to the 3/2, right? And so
That's just multiply, right? So it's just R cubed.
yeah, it's minus 1 over 2. Exactly, that's R cubed downstairs. R squared over R cubed is R, right? Minus 1 over 2R. And indeed, that is the mean curvature of a cylinder. We had that in a previous example. So in the case that A and B are both equal to R, it reduces to an earlier example, which is, that's nice. All right. So there's an example. To calculate the Gaussian curvature and the mean curvature, it's pretty straightforward, right? In the sense, like, there's nothing very ambiguous or like sneaky about the calculation, right? If you have the parameterization, you can just calculate the partial velocities, you calculate the partial accelerations, you construct the E, F, G, L, M, N, and then you use these formulas, and there it is, K and H, right? I mean, there's a lot to it, right? And for more complicated surfaces, these formulas get really, really bad, right? Because there's square roots involved. But at no point did we find ourselves differentiating a square root either. So they're not that bad. Other places in mathematics, you find yourself faced with like differentiating square roots. That didn't happen to us here. So it's bad, but it's not not, too bad. I have another example. Another example for you guys. Because I think it's healthy for us to do some examples in here of these, because the last 2-3 hours of lecture has been mostly just, here's the theorem, here's how we derive the formula, right? I want to sort of show you how we put it into practice. Okay, so the next one I'm going to do is a paraboloid. And so I'll do a specific one. I'll just do z is equal to x squared plus y squared. All right. And I'll use the usual parameterization where we use x and y as parameters essentially. So it's u squared plus v squared, right? And then we have the same goal. Our goal is to calculate the Gaussian curvature and calculate the mean curvature. All right? So what's the first order of business? We want to calculate xu, xv. I guess once we've calculated xu and xv, we can go ahead and get EF and G, right? That's what, 1, 0, 2u, xv, 0, 1, 2v, right? And so I guess we might as well calculate the cross product of these, right? So what's that work out to? Now, am I right, am I wrong? I mean, we can take the dot product of this. We get minus 2u plus 2u. The dot product with xu is 0. We get minus 2v plus 2v. The dot product of that is 0, right? So that should be the xu cross xv. The warping function, the length of this is what? I'm going to write the 1 first. 1 plus 4u squared plus 4v squared, right? That's the length of xu cross xv. So you guys tell me what is E, F, and G? Xu dot xu is 1 plus 4u squared, right? Xu dot xv is 0 plus 0 plus what? Plus 4uv. G, xv dot xv is 0 plus 1 plus 4v squared. So 1 plus 4v squared. Right? Now we can calculate the xuu is what? 0, 0, 2. Xuv is 0. Xvv looks like 0, 0, 2 again, huh? Now, note, the unit normal is 1 over w, right? Times the vector minus 2u minus 2v, 1. So now we can calculate the Lm and N, right? L is u dot xuu, m is u dot xuv, n is big U dot xvv. So what is that? What does that give us? Well, the looks like the x component and the y component in the unit normal don't even matter because they dot product with the zeros. And we just get like 2 times 1 or 2 times 1. But don't forget the 1 over w out front, right? So we get 2 over w, 0, and 2 over w again. And so, great, now we can put it together. Consequently, the Gaussian curvature is ln minus m squared over w squared, which in this case is what? Looks like m is 0. It seems like m is always 0 for my examples. That's just because my examples aren't too nasty. I get a 4 over w to the 4th power, if I haven't made a mistake. And so that's 4 over 1 plus 4u squared plus 4v squared squared. So that's the Gaussian curvature of a paraboloid, right? And what's the mean curvature? Let's see here. Well, the minus 2fm term is gone, but the GL and the EN term matter this time. So GL, we get 1 plus 4v squared times L, which was 2 over w, plus E, which was 1 plus 4u squared times 2 over w, divided by twice w squared. And so we can factor out the 2 over w, right? And we can cancel the 2's as well, right? We got a 2 here and here and here. Cancel the 2's. And you're left with 2 plus 4u squared plus 4v squared divided by w cubed, which is, 1 plus 4u squared plus 4v squared to the 3/2. So there you go. That's the formula for the mean curvature of this paraboloid. Now my question for you would be, does this formula for the Gaussian curvature, does it kind of make sense intuitively? If you can visualize the paraboloid, what's it look like? I mean, the paraboloid is one of these guys, right? And since u and v are x and y respectively, right? the formula for the Gaussian curvature written in terms of Cartesian coordinates is just this, right? 4 over 1 plus 4x squared plus 4y squared, right? Or if you wanted to write this in terms of polar coordinates, what it would look like. It's 1 plus 4r squared, isn't it? Squared. So I think there's a good chance that you could redo this calculation in polar coordinates and it might go better. Right? I mean, it's possible. Plausible. Does this formula make sense, though, is my question. As you think about the paraboloid, like where is it most sort of curved? Well, if you think about it, I think the origin is where it's most curved, right? Like that's where the surface is bending up away from the normal the most, right? And if you look at the formula here, k is biggest where? K is biggest, when x and y are both 0. We get a Gaussian curvature of 4. And then as you get away from the origin, the Gaussian curvature tends to what? As r goes to infinity, the Gaussian curvature goes to 0, right? So if you can kind of imagine, going out further and further away from the origin, you can kind of see how, locally, the paraboloid's getting more and more flat. Does that make sense? I think the formula does actually make a lot of sense if you think about what the formula means. And also the fact that it only depends on the radius also makes a lot of sense, right? Because there's a symmetry for the paraboloid where the polar angle doesn't matter, right? It should have the curvature should just be a function of the distance from the z-axis, which is r. So that also is a nice feature of our calculation. So yeah, a couple examples. There are, of course, more bells and whistles in Chapter 5, right? Like there's, the surface of revolution technology. There's like special formulas there that make for even nicer examples. I'll try to, when I, actually pick your homework problems, give you a little bit from the different sections. I'm probably going to steer clear of section 5.5, the implicit case, because I just don't think it matters to us that much, and it's kind of its own special world of different calculation. So I'll try to stick to the more mainline problems. But anyway, so when we pick back up here again, I'll start in Chapter 6, all right? So that's where we are.